Assalamu alaikum, grade 11 GED 2019-2020 students. This is topic 4, electric fields. Now we are continuing the second part of our lesson 4.2, concept of electric field and electric field strength. In this part, we are going to calculate the electric field strength at a point between 2 points, a 2-point charge, then determining the point at which the net electric field strength exerted by 2 points point charge equal to 0. Okay, now electric field between 2-point charges. Now we have here 2-point charges. Okay, this is 1, this is 2. There are some points between A is a point, B it's a point here, C a point here, D a point here. How to get the direction of the electric field at a point between between 2-point charges. Now, a positive and a negative charge, this is a positive, this is a negative, it's clear, with same amplitude, magnitude. It means this is K, Q, and this is Q. Same magnitude. Are on the same straight line as shown. State the direction of the electric field strength. So we want the direction of the electric field strength. Where? At A, B, C, and D. Now, to know that, we want, for example, suppose come to point A. We are here at point A. At point A, we have, this point is affected by 2 charges. There is a field due to this charge, positive charge, another field due to the negative charge. As we know that the lines for the negative charges are going inside. Yeah? The lines for the negative, this is for the negative charge. For the positive charge, the lines are going out of the charge. So this means that this point point A, affected by 2 charges. Now we are not talking about the force, we are talking about the direction of E, electric field strength. So you have to see here the field strength, the lines for positive are going outside and for the negative are going inside. It means A is under 2 electric field strengths which are in the same direction. For example, this is an E due to the positive charge, another E due to the negative charge, E1 and E2 for example. So that means the direction for E at point A always is toward right, because there is one due to positive charge and another one due to the negative charge. We have to add them and the direction will be also to the right. So it's to the right. So for A, it's toward right. Let's take point B. Here, point B. We have point B here. For point B, this is the nearest charge, which is positive. And you know the charge are going to be out from the negative. Yes? What about the effect of this charge, negative on B? It's very far. Anywhere, the lines are going into here. For the negative, they are going into the charge. But because we have same amount of charge, again going back to E equal to KQ over R square, we have the same amount of charge. That's why E only depends here on R. Whenever you have smaller R, you have stronger E. So the field at this point B, due to the positive charge, is stronger. So, okay, cancel this. That's why the direction will be toward left. Why? Because this field is stronger. Because it's nearest to point B. So why the field is here towards left? Because this is a positive charge. The field lines should be outside from the charge, like this, outside. So it will be toward here, left. Let's go to point C. Now we have here point C. Again, we have two equal charge with different distances. Here, the smallest distance, the charge is closer, and here the charge is farther. Of course, the effect of this charge will be more. So the direction of E at this point depends on the direction of E for this charge. For this is a negative charge, E should be into the charge, not out. Into the charge. That's why the direction of E here will be again to the left. Let's come to point D. This is point D. For point D, what will happen? This is point D, and this was a positive charge, remember. And this is a negative charge. For D, this is a positive charge. This should be the line for field. It is out of the charge or in. This is positive, so it will be out of the charge. This out of the charge. This is a negative charge. So if this is the line, yes, if this is the line that we are having, what will happen? The field will be into, or here it will be into the charge or outside. No, it will be into. So, sorry, this is the value, the direction of E due to this charge. So we are at point D here. There is an E due to the positive charge, and another E here due to negative charge. And you are, I think it's very clear if we have here a right angle between them, because the distances are the same here. This is a midpoint. Okay, so we have equal sides triangle. So as we did for the fourth, continuing, completing our parallelogram, this will be the resultant E at this point D. So this is the resultant toward right again. So it is toward right for D. Now let's go to calculate how to calculate the electric field strength at a point between 2 point charges. The same as we did for the fourth. So we have here a point P and two charges, a negative and a positive, and we want to calculate E at this point. To calculate E, we have to get E1 and E2. We have two charts. Each one is has the effect of electric field strength. So first of all, we have to calculate the direction of E due to each charge, Q1 and Q2. Suppose, okay, this is for example Q1 and this is Q2. So Q2 is positive. At this point, what will be the direction? The lines are going out of the charge. So it will be the direction of E. The lines going here out of the charge for this point. Here, this is a negative. At this point, lines are going into the charge. So this will be the direction of E2. Sorry, this is, if this is E2, so Q2 is E2, Q1, then E1. Is it okay? Now, how to calculate the net? We have to calculate each one of them, E1 and E2, and then they are in the same direction. We are going to add them. But the most important thing is to determine the direction of the field at this point P due to each charge. Here, charge is positive, lines are going outside, charge is negative, lines are going inside. Only we are seeing the effect at point P. The next point is to see what we have our Q1, Q2, are they in the appropriate units? Yes, coulomb. And we have R1 and R2. Our R1 is here 5 centimeters. So it will be 0.05 meter. We have our R2 5 again centimeters, so it is 0.05 meter. So, okay, we will calculate our E1. This, due to the negative charge, it will be okay, I think, okay, it doesn't affect either if it's Q1 or, we consider this as Q1, E1, and Q2, E2. It's okay. So our E1 will be K Q1 over R1 square. We have 9 times 10 to the 9 times Q1 is minus 5 times 10 to the minus 8 over, this is the distance, 0.05 whole square, and this is going to give us how much? No need even to substitute with the minus sign here, no need. For the force, we substituted with the minus signs just to know the value of the force, if it's negative or positive, yeah? If it's negative, that indicates that there is an attraction force, and if it's negative, positive, it means that there is a repulsion force. No need here to put the minus sign. So this is going to give us 1.8 times 10 to the 5 Newton per coulomb. This is our E. To the right. Let's calculate our E2. If this is our Q2, this is our R, for example, R2. So 9 times 10 to the 9 times our Q2 is 20. So it's 20 times 10 to the minus 8 over, again, 0.05 whole square. This will give us 7.2 times 10 to the 5 newtons per coulomb. And we have E1 and E2 both in the same direction. So our E total will be E1 plus E2 will be, we are going to add this with this, we will get 9 times 10 to the 5 Newton per coulomb, and the direction will be to the right, because both are to the right. Okay, now we are going to do the same, but if we have a point here and affected with two other charges, one is negative and one is positive, the point is not on a straight line between them. They are forming a triangle with right angle. How we are going? The same thing. First of all, we have to determine the direction of E1, E2. Suppose this is Q3 and this is Q1, and here, sorry, this is Q2 and this is Q1. Again, by mistake, it has been written Q3. This is Q2 and this is Q1. Let's deal with the small, the capital letter notations as you have in your formulas. Okay, now Q1 -5 microcoulomb and Q2 +3 microcoulomb, and we have the distances. We want to calculate the electric field strength and point or at point P, and with the direction. At point P, first of all, determining E2. This is a positive, so lines are going outside. Yes, so this will be the direction for E2. This is our negative Q1. So the lines are directed toward the charge. Yes. So here, this is a negative charge. Lines are going inside. So we have, this is our E1, E2 and E1. Now we want to calculate each one. First of all, let's make sure about our units. This will be 0.08 meter, 0.1 meter, 0.06 meters. Divide by 100. Then our Q1 is in microcoulomb, so multiply it by 10 to the -6 to convert it to coulomb. As we did before, Q2, 3 times 10 to the -6 coulomb. Just multiply by 10 to the -6 to convert from microcoulomb to coulomb. Now we are going to so we have to calculate E1 and E2. E1 equal to KQ1, this is the formula, over R square. So our E1 equal to 9 times 10 to the 9. Where is our, these are our, sorry, this is only Q. Okay. So let's be back here. Yes, this is only Q here. Okay, where is our Q here? We are talking about E1. This is our Q, -5. So it is without any minus. 5 times 10 to the -6 divide by 8 here, 0.08 with meter square. This will give us 7 times 10 to the 6 Newton per coulomb. Our E2, quickly, 9 times 10 to the 9. Where is our E2 here? So we are taking this charge, 3 times 10 to the -6, divide by, this is the distance, 0.06, so 0.06 whole square. This will give us 7.5 times 10 to the 6 Newton per coulomb. And now we have E2 and E1. Again, come how, this is our E1, E2, and E1 as you see here. To get the resultant E, they are both vectors, and perpendicular to each other. So we will complete our parallelogram, and this will give us the resultant E. And this is, as you see, as we have seen before, this is the hypotenuse. That's why we are going to use Pythagoras theorem to get E. So we have, this is the adjacent. We are talking about this triangle. So we have here two adjacent, okay, these are the sides of the triangle, this and this. And this is E2, and this is E1, the same here. So our E equal to, as we have seen before, because this is the hypotenuse, okay, so it will be the root square of E1 square plus E2 square. So it is the root square of, we have our E1, 7 times 10 to the 6 whole square, times E2, which is 7.5 times 10 to the 6 whole square, and this is going to give us the value of E, which is 1.03 times 10 to the 7 Newton per coulomb. Now we got the value for E total, or net E, or resultant E. How to calculate or to get the direction? Again, we are going to apply here tan theta, with this theta, tan theta equal to E1 here, the opposite side, E1, what is E1 here, this, so it is 7 times 10 to the 6 over the adjacent side here, E2, where is our E2 here, 7.5, yes, this, it is 7.5 times 10 to the 6, so we will get our sine tan theta. 10 to the 6 will cancel with 10 to the 6, so we want theta, not tan theta, so you have to do or get the tan inverse, or use the tan tan inverse of 7 over 7.5. This will give you the value for theta. Again, tan theta is 7 over 7.5. Okay, the powers cancelled. But we don't want tan theta, we want theta. So you have to get tan inverse, the value. This will give you the value for theta, which is 43 degrees. So this is making 43 degrees with E2. This is the direction. Now, how to get the point at which the resultant E equal to 0? We have here, for example, a point P separated by 5 centimeters from Q2, and another 5 centimeters from Q1, and you see they have the same values. We want to get E here at this point, because you know that E equal to KQ over R square. So this point is under, it has 2 electric field, it affected by 2 electric fields. The field due to Q1, what is the direction here? The field due to Q1, because this is a positive charge, so the lines are going to be outside here, this to the left, here to the left. and this is also the positive here, E1, and this is also positive, it will be to the right. Here, due to this charge, the lines are to the right. Why? Lines are going outside. Also here, from the positive, lines are going outside, here, to the left. So this is E2. So you see here, we have the same Q, the same R. From here to here, we have the same separation, and we have the same Q's. So what we are going to get, we will get here that E1 equal to E2. Yes? Because the same values for Q and the same separations from the point. So they are equal to each other and in opposite direction. So what will happen? The result of them, it will be 0. Yeah, and in opposite directions. So if we are going to get E and E2, E1 and E2 and subtract them because they are in opposite direction, you are going to get the net or the resultant E electric field difference will be 0. This point, this is the point at which the resultant force is 0. But what if we have two different, the same if we have two different, here, similar, it was there, positive was positive, here they are negative and negative. What we are going to get here, in the positive, opposite figure, determine the position at which the resultant E equal to 0. Because they are having the same values for Q, Q1 and Q2, okay, Q1 and Q2, and sorry, here we are not having the same value, but only we have similar signs. Okay, what will happen here? We have different values. So do you think that we will get the point at which E equal to 0 at the midpoint here? Of course not, because values are different. So we want to find the point at which E equal to 0. How to determine that point? This is what we are going to do now. Now, this is our, again, Q1, and this is our Q2. First of all, we have to determine the point where it should be. Now, if we consider a point here, P, point P, this is Q1, and this is with a charge with negative value. So this will be here the direction of E. E will be inside toward the charge. Okay, there is here charge Q2, and this is having a negative value also. So also E2 will be in this direction because it's toward the charge, inside the charge. E1, E2. So as you see here, we can get here again. It's very important to know if you have positive, positive and negative, negative, you can have a point in between where the net E equal to 0. If they are equal in charge, it will be exactly at the midpoint. But these are not equal. So we have to find where is the point. That's why I considered that the point is here, not in between. And maybe we can also, if the total distance between the charge is 20 centimeter, okay, we can consider the distance from the point to E1x. It means from the point to Q2, from point to Q1x, from the point to Q2, how much it will be? It will be the whole distance minus x. Yes, this was 20 centimeter, so it will be 0.02 meter. sorry, it's 0.2. It is 20 divided by 100. It will be 0.2 meter minus x. This is the distance from this point till here, because the whole distance is 20 centimeter. So we want to find what is the distance x at which here p at which e equal to 0. What we want to know, what we have to know, that at this point E1 equal to E2 and opposite direction. Yes? Yes. Okay. K Q1 over R1 square equal to K Q2 over R2 square. Yes? Okay. This K will be cancelled with this K. So we are left with Q1, which is minus 4. Again, Q1 is minus 4, and time 10 to the minus 6 to convert from microcoulomb to coulomb, and Q2 is minus 9, and multiply by time 10 to the minus 6 to convert to coulomb. So it will be 4 times 10 to the minus 6 over R1. What is our R1? The distance between P and Q1, which is x. We consider this x. Q2 is 9 times 10 to the minus 6. R2, this is R2. The whole R minus x will be 0.2 minus x. Again here, okay, now we want to find the value for x. This minus 6, 10 to the minus 6 will cancel with this, and we are going to left with what? 4 divided by x square equal to 9 divided by 0.2, sorry, this is also whole square, divided by minus x whole square. Okay, from here I think we can take the square root for each side. The square root for 4 is 2 over x square is x. Here square root is 3 for simplicity, over the square root for the whole bracket here, it's 0.2 minus x. Okay? Yes. Again here 3 times x, 3x equal to, this is 2 times, this is 0.2 minus x. This will be 3x equal to 0.4 minus 2x. Bring 2x here, it will give you 5x equal to 0.4. Yes. So x will be how much here? 0.4 divided by 5, and that is going to be 0.08 meter, which is 8 centimeter. So x will be only 8 centimeter from Q1. This is going to be here 0.0 meters, which is 8 centimeter. Hope that is clear to you. And I think what you can do here, if you have different positive, for example, a negative, and you are trying, okay, to here there is any point P, for example here, the direction for E, it will be outside here, it is outside, so it will be this side, E1, for example, if this is Q1, if this is Q2, and the direction for E2 due to the negative charge will be again towards, yeah, inside here. So we have E1 and E2 both in the same direction, so you are not going to get a point here in between where E equal to 0. Why? Because both have the same direction. So of course it will be somewhere here or here. You have to think about that and go through it. Try to find where it should be. Thank you. This was the end of our lesson. Thank you for following.